Hello, this is number 8, the lecture number 8 for this linear algebra series. So last time we have product of vector space and then quotient of vector space, and then we have stated these somewhat like the universal mapping property. Here, this is just the quotient map. And you can see this over and over again. If you have higher algebra courses, you can see this in the situation where your objects are vector spaces, objects are rings, or they are groups, or they are modules. Anyway, it's not, they are just and like I'm just giving some hints of what's going to be in the future if you decide to take those courses. So today, the topic is duality. So what's how we will start with the definition of a dual space and dual map. So as a introduction, we have here our notation for a set of linear maps, and this is a vector space. And if we have V to V, we can write this as V. So we call the set of linear operators. And then we have another special linear map from a vector space over F with the scalar field F. And then we call the element of this set of linear maps as linear functionals. So let us define them properly. Definition. We have a special name for this because they play an important role in linear algebra. These special linear maps called linear functional. So a linear functional on the vector space V is a linear map. Linear map from our vector space B to our scalar field F. So these are a linear functional. So we denote we can write this is the set of linear functionals. Which has, of course, a vector space structure. Let us give some examples. So suppose we get R3 to R. So this is a vector space over R. This is also vector space, but this is just the scalar field. To define P by following X, Y, Z an element of R3. It is mapped to 4X minus 5Y plus 2Z. So this is linear functional on R3. All right. So a more generic example is the following. If you get a function, let us generalize this to f to the n, and then this is to f, and then we get an element x1 to xn here. This is mapped to the product x1 x c1 x1 plus 2x2 plus cn xn. This is also, this is a linear functional on fn. All right. Let us define the set of linear functionals. This, we denote this with b prime, the set of linear functionals. All right. And then theorem, which is easy. The dimension of our v prime is just equal to the dimension of v. Of course, the proof is just the dimension of L, V, just the dimension of V as the dimension of F. Of course, the dimension of F is 1, the dimension of this is just dimension of V. This is an easy theorem, which is, it relies on our previous result. Let's now consider if we have a linear functional, a set of linear functional, we will define a dual basis. And this dual basis is in fact, as a theorem that we will state later on, is a basis for our v prime. Note that we will use b prime here. Some books use b star instead of prime, but it's just notation. So we define a dual basis. Let us consider a basis v1 to vn of, this is basis of v. The dual basis of v1 to vn is the least. Of elements of v prime, or is that of linear functionals, wherein this is defined as follows. P sub j of v sub k is just equal to the characteristic, the characteristic function. If this is if a is equal to j, and then this is if k is not equal to j. So these are linear functionals. Now let us consider the following example. If we get a vector space Fn, of course we have standard basis. The standard basis e sub 1 up to e sub n. Then what? E sub k is just 1, 0, k equal to j, k not equal to j. So these ones here is a dual basis of e sub 1, e sub n. Okay. So I will state this as a theorem that the dual basis is basis of our V prime. So I think I will leave the proof. So the proof is just to verify they are linearly independent, and then they span the entire B prime. All right. Now let us define a dual map. If our T here is a linear transformation from V to W, the dual map, here we will use the concept of linear functional, is a linear map T prime, an element of V W prime to V prime. Here our W prime and V prime, here is the ordering is reversed. And then this is defined as follows. The T prime gets an element of W prime. It's just the composition of W prime with T for all omega phi. It's not W prime, phi in W prime here. So, okay. So, this T prime here is the composition of the map phi and T. And T is indeed a linear map from V to F. So we have here, this is a linear map from W to F. And then here we have a linear map from V to W. So you get from V to W, and then here it goes from B to W, and from W it goes to F. So this one, T prime here, is an element of the linear map from T to F. That is, T prime is an element of V prime. Right. So uh, verify that T prime is a linear map by showing that this is linear, and then the homogeneity is satisfied. Okay, so let us give an example. So this is a little bit new concept. Consider the D from the vector space of polynomials coefficients in R to polynomials with coefficients in R the same, where you get D of P here is just equal to the first derivative of P. Now, suppose that is a linear functional on the polynomial ring with coefficients in R, And then this is defined by P of 3. They get this just to get the polynomial and evaluate it at 3. Then your d prime of P. Here d prime is the linear dual map of the d prime of P of evaluated at P is just the composition of V and D evaluated at our polynomial P. So we just have the linear function of phi evaluated at d of p here. What's d of p? D of p is just p prime. So get this, and then we get the evaluation of p prime at 3. So in other words, our p is a linear, d prime, I'll write this properly, d prime of phi is a linear functional on the polynomial with coefficients in R. So what this polynomial this linear functional does is it takes our polynomial p, and then the output, it takes it to the derivative of p evaluated at the number 3. All right. So let us now go to some algebraic properties of dual map. So number 1, we have S plus T, and then you get the dual. It's just getting the dual of S plus the dual of T. This is for all S and T in the second one. If you get lambda T prime, it's just lambda and then T prime for all lambda in our F and for all T in V to W. And number 3, if we get S T prime, we get T prime first and then S prime for all S and T element of LVW. Oh wait, this is a composition, so S here and T comes from different. Here our T comes from L U to V, and then our S from L from V to W. So this one is L U to W. The proof here is just straightforward computation. So as I remarked earlier, some people use this. But in case that you want to use this in future courses, just be sure that be consistent with your notations. Okay. Now we go to the slightly complicated things, the null space and the range of the null space and range of dual. maps. So our goal here is to describe null T prime and range T prime in terms of the range and the null of the original T. So, but first, let us define an annihilator. We will denote that as U raised to 0 or U 0 or U null. So you get U subspace of a vector space V. The annihilator of U here denoted U0 is defined as follows. So you just get the elements of the linear functional on V such that if we evaluate the linear functional at the number or at the element U for all U in the subspace U, you get 0 here. Okay, let us give an example to illustrate U0. Suppose U here is just subspace of our polynomial with coefficients in R, and U multiples of x squared, and then we get this is a linear functional on our polynomial ring, and then we define this as to get a polynomial is just get the derivative of the polynomial, evaluate it at 0. Then what you get is that our P is an element of U0, because here if you take the derivative of all of any elements of this subspace, you remember that this subspace U has lowest power of x is x squared. So the derivative of x squared is 2x, and then you evaluate it at 0, you get always 0. Okay, so yeah. Here, so to explain that further, suppose an example element of U, your big U here is x squared. Let's make this R. We have x squared, you have x to the 4 plus 3x u plus 5x squared. So if we get the derivative, we get here 2x, and then if you get the evaluation at 0, you get 0. Here we have some, using derivative, we had some for this, but there's an x also, and then we get the 10x, and then if we evaluate it to 0, it will become 0. That means this P here is an element of the annihilator of the subspace U of our vector space of polynomial with coefficients in R. Okay. So for the annihilator is a subset of the dual space, and your U0 depends on the vector space containing U. So the notation should be, if not clear, we write U0V here, the vector space, and then here where U is a subspace, and then U0 is a vector space. And in fact, no, it's not a vector space. This is a subset of the dual space V prime. Now let us consider an example that will give us insight. I give the structure of an annihilator, but let me give an example to illustrate the scenario. The proof is just a generalization of this example. Suppose we get R to the 5, and then E1, E2, E3, E4, and E raised. This is basis. This is the standard basis of R5. And then let E1, E2, E3, E4, E5 be the dual basis as I described earlier. Suppose that U is the span of our vector E1 and E2, the first two element of the standard basis. So this is just the span is just x1, x2, 0, 0, 0, and then x1 here and x2 are elements of R. So these are elements of R5, of course. So what we want to show is that the span of this one, E3, E4, and V5 is equal to our U0, or the different, or your U0 is equal to this span. Okay. Now, how do we show that? So here, solution, we know that this is the linear functional takes x1 up to x5 here, you get x sub j. Okay. Recall. Now, suppose that your linear functional is in the span of these three. Then we can write the linear functional as C1, let me write 3 instead of 1 for consistency. C4 plus C5, where C's are elements of the field F, not F, but in this case R. Okay. All right. If we get your x1, x2, 0, 0, 0 element of U, then your y evaluated at x1, x2, 0, 0, 0 is just evaluate this map here at this point. So we get this evaluated at this one evaluated here we don't have, so it's just 0, we get 0, we get 0, and then we have 0 here. Okay, let me write it a longer one, a longer form. So you have C3, and then V3 plus C4, V4, and then C5, V5, then evaluate it at x1, x2, 0, 0, 0. So here goes this C3, the partner here are zeros only. For x1 and x2, there's no partner. So you note that for the definition, you get C sub j, X sub j, but here, evaluating further, we get 0. What this means is that this is an element of u raised to 0. This means that the span of 3, 4, and 5 is a subset of u0. Now, we want to go prove the reverse direction. Suppose that this is an element of u0. Okay? And then we can write this as C1, C2, C3, C4, C5, because CIs are and R, because these are the bases of our R5 prime. Okay? Now, because your E1 is in U, and in U0 we have E. If we evaluate at E1, this is 0, and this is just C1, and then C2, and then C3, and then C4, and then C5. Evaluate it at E1. So this one and this one magiging 0, this one will be 0, this one will be 0, because this one here is not the same with this, not the same, but here this is just the same. So we just get what? C1. Okay. Note that this is 1 in the first, this is 1, and then 0 all else, so we just get C1. Similarly, for E2 element of our U, we get C2 is equal to 0, and so forth up to what? Up to C5. So here, all of the constants C1 to C5 are 0. Okay? Not all. We just not all, because what? I made a mistake here. We just end with we get because they are just 0. Now we get this one here, this E3 is not in U0, E4 is not in U0, and E5 is not in U0. So we get this P here is just linear combination of C3, then C4, and then C5. That means that U0 here, this means this is in the span of P3, P4, and P5. And therefore, your U0 is just the span of 3, 4, and 5. So end of the solution. I think it's not end of proof. So we have basically, so motivating is further, we will state our theorem that your U0 is a subspace of your V prime. The proof is easy. U0, the zero map, the zero functional is in U0. And then if you get this and this in U0, we get this of U is equal to this. No, I missed notation. This of U, this is all 0 for all U here in the space U. Thus, we get evaluate U, we get 0 because of the linear property. And also, this is for the closure under class, and also for this is first check. Right, this is check 1, check 2, and check 3. Also for a scalar multiplication. You have to check this one. Okay, I think that is just an easy proof. Now we go to the dimension of the annihilator. Theorem. The dimension of U plus the dimension of the annihilator is equal to the dimension of the vector space V, wherein here U is an element and a subset of the vector space V. So the proof here relies on the fundamental theorem. Linear maps. And I will leave that as reading exercise. Now, we go to this important theorem, which we will prove, and then we have a similar counterpart for the range, which we will leave as an exercise. The null space of your dual map T prime. Okay, so suppose V and W are finite dimensional vector spaces. And then T here is an element of V to W linear map. Then your null of T prime is just the range of T 0 and letter B. The dimension of the null T prime is just the dimension of null T plus the dimension of W minus the dimension of V. Okay, let's prove the first part, letter A. So suppose we get an element of the null T prime. Because this is in the null, this is just 0. So this is by definition. Hence, we have 0 is just of V, which is just E of V for every V. This means that this is in the range T0. So this is the range T, and then if you get this is equal to 0. So this is in the annihilator of range T. Okay. Now, this implies, hence, your null T is subset of range T 0. For the reverse inclusion, suppose that you have here an element of range T annihilator. Thus, you get this is the range, or this TV is equal to 0. Here, this is an element of the range for all V in the vector space V. Hence, we get 0 is just T, right? This is equal to T prime. That means your phi here is an element of the null space of T prime. Thus, finally, we get the null of T prime is just, this means your reverse inclusion. Ano nga yan? Range T is a subset of null T prime, and therefore this range T annihilator is equal to null T prime. Now for the B, it also relies on the fundamental theorem. This is easy. So the dimension of the null T prime is equal to the dimension of the range of T annihilator. Now, this one is equal to the dimension of W minus the dimension of range of T. Since T here is a subspace of W, and then T annihilator is also subspace, so from the above equality, we get this. And also, since the range is just of T is just the dimension of the range is just the dimension of V minus the dimension of the null T. So we just have W here is just the dimension of V minus the dimension of null of this T here. So rearranging, we get the dimension of, okay, T plus the dimension of W minus the dimension of V. And then this ends the proof. And of course, the reason I just say it loudly. Okay. Another proposition is if T is what? T is surjective if and only if T prime is injective. So the proof here is as follows. T is an element of LV to W. Surjective if and only if your range T is equal to W. So this is definition. This happens when, this is if and only if your range of T annihilator is just trivial. This happens, trivial yung annihilator if and only if your null of T prime is just 0, which happens if and only if your your T prime is injective. So that's the proof. And then there is a similar state parallel statement on injectivity of T and the surjectivity of T prime later on, which I will not prove. Now, we go to the range. With the same assumption, we get the dimension of the range. T prime is just the dimension of the range of T. And letter B, the range of T prime here is just the null space of T, the annihilator of the null space of T. So we will go with the easy part first, which is the letter A. So the dimension of the range of T prime is just dimension of W prime minus the dimension of the null space of T prime. So we get the dimension of W prime minus the dimension of is the range of T0 from what we have earlier. And what is this? The dimension of W minus the dimension of range T, and later we get the dimension of just the range of T. Okay, the reasons I just stated. So just feel free to keep track of the reasons. Yeah. For letter B, I will leave the proof, but it also relies on showing the double inclusion. Now, for the similar statement on the if T here is injective, this means that our T prime is surjective. So the proof here is similar if and only if statements. So T is injective if and only if your null of T is just the trivial. This means if this happens if the null of T0 is the entire dual space of V, which happens if and only if the range of T bar is the entire V prime. And then this means if and only if T prime is surjective. And this ends the proof. Okay, now we will go to the matrix of a dual map. First, we recall that we can construct a matrix of a linear map. Now we will construct a matrix of a dual map. So let us define first transpose. We get a matrix A, the transpose of A denoted A transpose is done by obtained by interchanging rows and columns. So if A is M by N, A transpose is N by M. And the entry is as follows. If you have our matrix is this, A transpose, the K jth entry of the A transpose is the A, the j kth entry of the matrix A. An example, this is familiar from your linear algebra. I mean, if you have matrix and matrices before, this is familiar. This is our A, then A transpose, you just get this is 5, -7, 3, 8, and -4. So that's easy. And then transpose here has nice algebraic properties. And as so properties here, the properties for addition, just A transpose plus C transpose. Also, if we have lambda A transpose, you get lambda A transpose. However, if you get product, I think you are already familiar the product. So let's call this a theorem or some proposition. So now I'm just calling it theorem. So if we have a C transpose, get A transpose, and then C transpose first. Okay. So how do we prove that? So AC transpose the KJ entry is equal to the AC J entry of AC. This is just equal to the sum of A J R C R K from for R from 1 to N. And then this is just equal R from 1 to N of CT KR and then AT RJ, which is equal to CT AT KJ as desired. So why is that so? Because this is the basically on the algebraic properties of multiplying matrices. This is if you will show this, it's like hard to picture out, but doing it in small matrices, it's very obvious. So I'll not be doing this very details. Now we get, how do we get the matrix the transpose? Again, I think the matrix, this theorem is the matrix of the dual map. T is just the matrix of T. You get the transpose of that. Okay, so the proof here is a little bit long, but it's the same with the line of argument that we did here. So basically, the bridge that may be vague on your part is how this and these are transformed, so which I will leave to you as exercise. So notice that here, if you get the transpose, you have this will go first, and this will go second, and then these ones and these ones here will also interchange or their ordering. Basically, if you transform the column vector and the row vector, it's something manipulation on that kind of stuff. So here I will just leave the proof as an exercise again. But just remember that this one is the matrix of the dual map T is just the transpose of the matrix of the original map T. So now I think I'm tempted to finish this one at this part here. I think I'm a little bit this lecture is long. I think I'll end here and say what's coming up next for our lecture. So we will start next meeting with the rank of matrix. So this ends this chapter. The on duality. On the next one, we will consider, I will be skipping the chapter on polynomials, and then we'll just recall some notion as the need arises. We will go directly to, next meeting, we will go directly to eigenvalues, eigenvectors, and then others other related notions. So I think I'll end the discussion here. This proof here is a bit long again, but it's just routine calculations. Thank you.